thank you about saying about those opportunities at IIIT Delhi, sir. In fact, I've seen some of your posts on LinkedIn wherein you mentioned about PhD positions at IIIT Delhi in your team. So I guess students
Yes.
will benefit from finding those posts on LinkedIn whenever
Yeah.
they
So
can.
they can always they can always check out my profile on LinkedIn. It is Anuj Grover. So they can always do that, and they can connect with me, and they can always be updated about the kind of work we are doing and the openings that we have in our teams.
Yes, sir. Interesting. And apart from in-memory compute, so what are the other advancements that have been going very recently in memory circuit design? So you could share if you have any in your.
Yeah. So in-memory compute is one dimension of work, Neeraj. Another dimension of work is related to. Okay, so let me take a step back. So when we talk of in-memory compute, that is enabling and making our portable systems much more energy efficient. So do you know that Google Alexa or uh, you know Alexa and Google Home, sorry, Amazon Alexa and Google Home, what they do is they actually transfer all the data, all the voice that you write, that you speak to it. They send all the instructions back to the cloud. They process those instructions there, and then the output comes. That is not actually required. And you cannot really have IoT in this manner if you have to operate real-time systems. For example, if you to talk about security, what if the people who are sabotaging security actually just cut the internet connection? Then all your smartness of security camera would go away, is it not? So we want calculations, we want processing to be done at the edge. So when we say that I'm working on in-memory compute, that is the kind of applications we are enabling, making our lives smarter and not dependent on the cloud. Okay, doing much more computing on the edge so that we can be more and more resilient. The other dimension which touches our lives in a very big way is electrification of cars. So, 20 years back or 30 years back, there was hardly any electronics component in a car. Today, a new car could have up to 1,000 electronic chips in it. Do you know this? More than 1,000 electronic chips in one
Yes,
car.
sir. Yes, sir. True.
So the overall bill of materials, electronic bill of materials of the cars is increasing tremendously. Now, this is a good thing for the electronics industry, but it does not come cheap. It does not come easy. For example, when we talk of a cell phone, let us say your cell phone hangs up for 2 seconds. You will simply wait and you will let it come back. Am I right? Suppose it did one wrong calculation. Suppose there was a small blip in one of the pixels of the image that is being rendered. You will probably not even notice it. Am I right? Now, imagine that the car that you're driving, there is a system that is calculating the amount of braking that needs to be done. Because it is measuring the distance from the car ahead of it. We're talking about self-driving cars or more intelligent cars. It is measuring the amount of or the distance between yourself and the car ahead of you. And then based on that distance, it wants to apply brakes. In that calculation, applying brake meant minus of acceleration, and acceleration would have meant a plus sign. Just one bit. The positive and negative integers are differentiated by only one bit in our number.
Yes, sir.
Suppose that one bit gets corrupted. Instead of slowing down, do you realize the car would accelerate and there would be a huge crash that would happen? It's no longer one pixel not being rendered properly. It is a matter of life and death. So when we talk of using of electronics in automotive industry, there is a big challenge of ensuring the safety. So there are standards for safety, ISO 262 standards for safety of each and every component that goes into cars. And when electronics goes into cars, there are very stringent standards for safety for electronic components also. We call them ASIL A, B, C, D, and so on. So for components that go into braking, acceleration, fuel injection, coming up of the airbags and so on, these are life critical functions. So chips and components that go into these parts of the car, they have to be ASIL D certified. ASIL D means that you are extremely error resilient. First, so you're error resilient in the sense that even if an error happens, you're able to recover from it. And not just that, you also have the capability to preempt an error, to predict an error. That, okay, now since aging has happened, or now since this thing has happened, I predict that there could be an error, or I predict that this could be the error rate, and so on. So we are working in our team on diagnostic circuits, which can themselves raise a flag, raise a hand and say, oh, while I calculated this, I made this computation, there's an error over here. I know there's an error. While you ask me to access row number 25 in a memory, I tell you I have accessed row number 28. So there's an error. Please don't use this data. So we want circuits and components to raise a hand and say, oh, I'm in error. Please ignore my data. Either redo the calculation or use calculation from my friends. So typically in such life critical functions, we use what is known as triple modular redundancy. So instead of one processor, there are three processors. So once the memory in one processor or a circuit in one processor says, oh, there is an error, then we know this processor's output has to be ignored and that of other two has to be used. So as the technology is becoming more and more advanced, as we are scaling further, the probability of errors creeping into more than one core is increasing day by day. So we have to be much more careful. TMR may start to fail. Even with TMR, we will need to add many more features which would not only tell that there is an error, but also predict that there could be an error in the next cycle or in next 100 cycles or so on. So in our team, we are working on circuits which estimate the reliability, which kind of measure aging of the device. So it's interesting work that we are doing in the domain of safety. So we are working on circuits which raise a flag, and we are working on circuits and systems which also measure aging and then predict that, oh, now since aging has happened, you can expect more errors. And since you are getting more errors, next time you go to the service shop, you better get the motherboard changed. You see? So when you now dock your car into the service station, the service engineer would know that, okay, this particular chip on this particular board has started to age and it is no longer safe to allow it to be there. So all that predictive maintenance and all these things are going to be the norm going forward. And that is what we are working on. In addition to, as I said, in-memory compute. So again, there are design openings, there are research openings in this area. Those who are interested can join in.
Sure, sir. And that was in fact quite insightful about the work that's going into memory design very recently. So in fact, I can relate with your answer, especially the security thing that you talked about, the one bit flip with deceleration or acceleration. That was actually critical. And I've read a paper where they talked about DRAM memory bit flips. So how could that affect? So
Yes.
security is an important, very important aspect, as you told. Yes.
Yes. So we're also working on security. So, I'm not sure if you are aware, but your processor consumes a different amount of power when it is calculating something with a 0 than when it is calculating something with a 1. And
yes, so can you just brief us about it, how it's different? I mean, in simple words.
Okay, look at it. Let's say we are adding two numbers. One is 1000 and the other one is 1111. So you will see that when you add these two numbers, only one bit generates a carry. The MSB generates a carry and nothing else. So there is one kind of power consumption. Now consider you're adding 0, 1, 1, 1 and 0, 1, 1, 1. So every bit will now generate a carry. So, or let us say 0, 1, 1, 1 and 1, 0, 0, 1 or something like that. Every bit will generate a carry and the power consumption profile will be very, very different. And people can actually trace the power that you consume by doing backside imaging of your chip. So what they do is they thin away the chip and they just see where the heat map is. And they can know what kind of heat is being generated. So what kind of energy is getting consumed, they can find out. They can give parasitic vectors to understand the data that you are using, the keys that you are using, and so on. So that is a big challenge when you talk of cryptography or security. So there is one beautiful thing in memories, Neeraj. It is that whether you read a 0 or you read a 1, the memory would consume the same amount of power. Like you can have memory architectures where whether it is a 0 read or a 1 read, whether you're writing a 1 or a 0, it consumes the same amount of power. So we built upon this premise that, okay, memory by its very nature is data agnostic. It does not change power consumption based on 0 or 1. At least we know there are architectures which are data agnostic. And we use such architectures to design a in-memory compute paradigm where security algorithms were embedded such that hackers can no longer distinguish between 0 and 1 estimations. And we're doing calculations inside the memory. We have designed adders, we've designed other circuits, which are again data agnostic. And we're doing that kind of work also. So security is also something which is hot, and we are at that too. So we have a good group, we have a big group, and a lot of students, I don't know why, but there are a lot of students just come and work with me. So I'm able to do work in different domains. And I would welcome you also. If you would want to do something, do some research, we can find projects and we could work together.
Yes, sir. Thank you so much, sir. And in fact, it was quite insightful and knowledgeful as well, what you have just talked about memories. And I guess students who some of whom didn't know you before, maybe they'll get to know now with this session, and they'll join you on your team.
Yeah. I look forward to that. I welcome the students.
Yes, sir. Thank you so much. Yes.